Well, good morning, everybody. We are meeting after 2 weeks, and the last time we are discussing the your third module, which is the stress-strain relationship. What is the stress-strain relationship for linearly elastic solids itself? What we have noted in this particular subject, solids mechanics, we are interested to know the stress condition and strain condition of a particular point of the solid itself. Now, we know strain components are related to displacements, and we have formulated 6 Cauchy's equation between the stress and strain itself. Now, 6 of the what we will discuss the relation between the stress and stress component, which terms as constitutive equation itself. Now, we will discuss the relation between stress and stress components I have just told you. This relation is particularly defined as the stress and strain displacement equation itself. What shall we discuss? We have already discussed it, the relation between strain and strain components now, which is termed as the components of this constitutive equation itself. It depends totally on the manner how which the material resists the deformation itself, how much it will deform, or what is the amount of strain and what is the amount of stress for which this strain is happened. Now, what we are going to deal with in this particular chapter, which I have discussed, which is defined as the constitutive equation, and are the mathematical description of physical relationship, physical phenomenon based on experimental observation itself, and which is so it is nothing but the mathematical derivation itself. Now, what we have described here, they will actually what we have trying to make this stress condition at a point and strain condition at a point of a particular solid itself, which is under external load. What we have done in the strength of material class in your third semester is we have already discussed a cross section and over which the stress and strain is uniform throughout the length. And based on this approximation, we have discussed so many things, but here we are trying to define to know the stress and strain of a particular point of the cross section itself, which may not be uniform throughout the length of the cross section. This is the basis of so many discussion here in this subject of solid mechanics. But here also you are looking for a lot of approximations or making empirical formula itself, where we are taking a lot of relaxation, you can say, for the case, in order to reduce the excessive complications in making the mathematical models for stress and strain itself. Now let us discuss the Hooke's law itself. Let me share. Next, what is the general statements of Hooke's law? Hold on. By definition, we know Hooke's law is stress proportional to strain itself, provided the concerned member is within elastic limit itself. Now, as we know from the experimental observations that the elementary length of the material, the axial stress sigma is proportional to the axial strength epsilon. Means stress sigma is proportional to strain epsilon itself. Now, of course, within the elastic limit itself, and the constructed proportionality is defined as the Young's modulus. This is all known factor, sigma x. Acha. Now we know that in case of uniform rod when it elongates, there is also lateral deformation, which is take place, which is defined as lateral deformation. Lateral deformation, which is accompanied by any longitudinal deformation itself. And lateral deformation is also proportional to the longitudinal deformation. This constant of proportionality is defined as Poisson's ratio. Now, this what we will explain here now. We will extend this information of knowledge to relate 6 rectangular components of stress to 6 rectangular components of strain. And we assume that each independent component of stress may be expressed by a linear function of 6 components of strain and vice versa itself. These mathematical statements expression of the statements are the stress strain and strain components. Now here what we have here is 6 equation in terms of sigma x, sigma y, and sigma z, and shear, which is the longitudinal stress in x, y, and z direction, tau xy, tau xyz, and tau zx, which is the shear stress existing on xy plane, yz plane, and zx plane itself. And this is related to the strain along x-axis, y-axis, and z-axis, and also as shear strain along xy, yz, and z-axis, and which is also given multiplied by so many empirical constants A11, A12, A13, and A14 and A16. Conversely, we can have the same equation in terms of f psi xx in case of sigma x, and sigma x, sigma y, sigma z, tau xy in case of f psi xx, f psi yy, and f psi zz itself, where this A1, A2, A3 all are constants on a given material. Now, question is, we have to solve 6 you have to solve this equation 2, means this 6 simultaneous equation, and we also get 6 equation 3 and vice versa itself. Now, these 6 equations of 2 and 3 are known as generalized Hooke's law itself. And whether we can use this setup of even equations or that given in equation 3, constant are approximately involved itself. Now, what is important here? In order to know the relation of stress and strain, we are supposed to know all these 56 what is this 6 multiplied 36 constant A1, A2, etc., which is vertically virtually impossible. So here also you have taken into account of various approximation whether we can reduce this number of equation and whether we can get a more usable, understandable, and usable set of equation to know the relationship between stress and strain at a particular point itself. In order to use this position, we have to take into account 2 particular properties of the concerned material itself. Now, what we have to do here, we are here defining 2 properties of the system itself. One is isotropic property of the material, and isentropic property. What is isotropic property? A material is said to be isotropic when it's a particular stress in a particular point in uniform in all direction. All. So stress a particular point over throughout this anywhere in this cross-section area or anywhere else, it has same stress in all direction, means either x direction or in y direction or z direction. And what is isentropic property is the stress and stress is after a particular point, it is of homogeneity, stress and strain property, which is same at all points. Means stress and strain properties are same in all points. That is the isentropic property. Means here for isotropic, we know for a particular position, the stress is uniform in all direction, and here in isentropic property, the stress in all the points are same, but they may not be uniform in any direction itself. But here, for a particular point is uniform, but stress may not be uniform for all points. And using this particular isotropic properties itself for our future course of action to reduce the number of constants like here. Just 1 second, please. Just 1 second. Now, we are here assuming this, the material is isotropic itself. One can show that only two independent elastic constants are involved here in the generalized statement of Hooke's law. What are they? Independent elastic constant. We have seen this stress analysis that any point there or plane on which the resultant stress are wholly normal. At any point there exist, at any point there may exist three faces or planes on which the resultant stress is perfectly normal, and there is no shear stress in this point. I am repeating again. For it in a universal in space of any particular material on any point over it, there will always exist three faces or planes on which the resultant stress are perfectly normal and wholly normal, and there is no shear stress exist on this plane. These planes are defined as here the principal strength itself, and the stresses on this plane are principal stresses. That these are the principal strengths, and the stresses on these planes are principal stress. That is principal plane, stress, and principal plane. We know every plane is defined by a normal over which this plane is acting itself. So always these principal planes are being associated with a normal with the normals, which is lambda over these three particular planes. What we are assuming here, we have three principal planes where with the stress there is no shear stress, and each principal plane has a normal in it. And so we are imagining a normal is the origin O, over which we have three stresses like this, three bars like this, X, Y, and Z. And these stresses, these OX and Y and OZ, are normal to one each of the principal stress plane itself. So there is no shear stress acting over this part itself. So it's, as it is an isotropic material, here the stress is uniform on any direction itself, particular direction itself. And if we say the principal stresses are, say, sigma 1, sigma 2, and sigma 3, and principal strengths concerned are epsilon 1, epsilon 2, and epsilon 3 itself. Now, for the principal stress, sigma 1 becomes sigma 1, the equation, thus the equation which we have discussed just earlier, sigma 1 is supposed to be the A1, epsilon 1, A2, no, sorry, this is B, which is A, epsilon 1 plus B, epsilon 2 plus C, epsilon 3 itself. Now, where A, B, C, these are all constant. Now, as we are saying, the principal stress, we are doing everything on a isotropic plane itself, where isotropic plane, the material is isotropic itself, so strain is informed all in all direction itself. So thus we can say this this constant B and C is supposed to be equal, so that the effect of sigma 1 in the direction of epsilon and epsilon 2, both at right angles to alpha, must be same for isotropic material. Here we are saying B is equal to C, so the effect of sigma 2 and sigma 3 is more or less same. They are acting, say, one of them is acting in Z direction, another is acting in Z direction, but their eccentricity is more or less same itself. Thus, what we are doing here, here ABC, these are constant. You observe that B and C should be equal, since the effect of sigma 1 in the direction of epsilon 1, 2, and which are both at angle alpha must be same as isotropic material itself. So sigma 1, the equation becomes sigma 1 A epsilon 1 B into epsilon 1 plus epsilon 2. As we are saying that, just we have already that B is equal, B1 is equal to B is equal to C. So if we simplify it further by introducing a term minus B epsilon 1 and plus B epsilon 1, this equation will take the form A minus B epsilon 1 plus B multiplied by epsilon 1, epsilon 2, epsilon 3. Now, just we are adding and subtracting this position B epsilon 1 itself. But epsilon 1, epsilon 2, epsilon 3 is the first invariant of the strain J1. This is invariant, and or the cubical strain J1 or cubical duration delta 2. We have already discussed this situation in our first stress point of view, what is in the and denoting by lambda and A minus B by 2 into mu, equation 1 as reducing as lambda sigma 1 is equal to 2 into mu 1 A minus B is B1, so that is 2 into B1 into epsilon 1, and delta lambda is equal to epsilon 1 itself. Thus, this becomes equal to lambda into delta and 2 plus 2 mu into epsilon 1 itself. Similarly, for epsilon 2 and epsilon 3, we are getting sigma 2 lambda sigma plus 2 mu into epsilon 2, and sigma 3 sigma lambda lambda sigma multiplied by 2 into mu into epsilon 3 itself. These three equations are supposed to be equally important for our next subject point of view itself. Delta, so delta. What we are doing here is we are putting epsilon 1 plus epsilon 2 plus epsilon 3 is equal to lambda, and replacing B by the term by delta, epsilon 1 plus epsilon 2 and epsilon 3 by delta itself, and we replacing the T term B by the equation lambda itself. And here A minus B we denoted by 2 into mu into epsilon 1. So both these three equations we can epsilon 1 principal stress, 1 sigma to another principal stress, sigma 3, the third principal stress itself. Now, thus instead of 36, we have only two elastic constant involved in the relation between principal stress and principal strain for an isotropic material. So, what is our assumption first? The material is isotropic, means it has strain for a particular point. It has same stress or same strain in all direction. Thus, we are reducing. Then we are using the terms the lateral deformation and lateral strain, and equating the lateral strain in two particular other than x, y, and z direction. We are equating the lateral strain as same, and we are thus reducing the equation to a considerable extent behind that. And this can be extended to relation between regular, rectangular, and straight component also. Now, let the coordinate axis OX, Y, and OZ coincide with principal stress axis itself. What we have here, what we are doing here, we have the coordinate axis OX, Y, and OZ are coincide with the principal stress axis. It coincides with principal stress axis. What is the benefit of it? We are having this equation like this: OX and OY. Drawing is horrible by my side. So that is Y, and Z, that is O. And this OX, Y, and OZ is according to the three principal. According to this OX, Y, and OZ are three principal axes, which are normal to one each to the one principal strain itself. And this definition is there is no shear stress along this particular OX, Y, and OZ axis itself, as they carries only the principal stress. Now, let us consider another strain, orthogonal frame of stresses originated from the origin O itself. That is, say, it may look like this: OX dash. It look like this: OY dash, and also may look like this: OZ dash. So what we have here, this OX dash axis has is creating certain angle with all three x, y, and oz axis. So it has the direction cosine, which is the cosine of the angle subtended by the terms x, which is the angle subtended by the straight line OX with OX dash with OX, Y, and OZ itself. Then these reaction cosines of OX dash, reaction cosines are NX1, NX1, NY1, and Z1. And the Y dash reaction cosines are NY, NX2, Y dash, NX2, NY2, and Z2. So, as we know, X dash and Y dash are at right angles to each other. We know that their multiplication of their individual reaction cosine will be equal to 0. That's we are having NX1, NX2, NX1 into NX1, NX2 plus NY1 into NY2 plus NZ1 into NZ2. This relation is equal to 0 itself. Now, what we have here, there are components, the normal stress that we can consider what this newly orthogonal axis OX dash, OY dash, OZ dash is. It has normal stress and sigma stress and versus shear stress across. We have across it along them or over in plane itself. While sigma x dash is the normal stress along x dash direction, and tau x dash y dash is the normal strain, is the shear strain along sigma x1 dash, sigma x dash, and tau x dash y dash is the normal and shear stress of the particular line OX dash itself. And if we can, this is available from the Cauchy-Swan formula which we have discussed in stress and strain relation itself. Now, what happens? This resultant stress vector on the x dash plane will have the components of nx1 sigma 1 and nx2 that is going on tx just 1 second. So what we have, that is Tx Tx to the power n is equal to sigma x. It's creating a problem. Now, the normal stress sigma x dash and the shear stress tau x dash y dash VAC, we are obtained from Cauchy's formula in the strain analysis itself. So what we have here, the resultant stress vector in the x dash plane will have the components as the resultant as Ty x dash is equal to nx sigma y Ty x dash ny sigma 2 Tz x dash nz sigma 2, which means we know we have three principal stress acting along OX, and as sigma 1 is along OX, sigma 2 is along OY, and sigma Z is along O3, is along sigma 3 is along OZ itself. Now, our new coordinate axis OX dash Y dash Z dash it is shifted or keeps its origin at O itself, but it is shifted from the principal axis to a certain extent, and the angles subtracted by all the individual OX, OY, and OZ are, we have already defined the direction cosines in terms of NX1, NYY, and Z1, etc. itself. Now, this principal stress sigma 1, principal stress sigma 2, principal sigma 3 has component along this x-axis OX dash, OY dash, and OZ dash. And these components are here given as sigma 1 multiplied by the reaction cosine, which x-axis takes with the OX direction, sigma 2 multiplied by reaction cosine ny2, where it is subtracted from the OX itself, and sigma 3 multiplied by nz2, which is subtracted by the distance itself. Now, these are the components in x, y, and z direction. The normal stress on this x plane is obtained. The normal stress on this x plane is obtained now as the sum of the projection of the components along the normal stress. So normal stress will be again the sum of the projection, means we have to multiply this by nx1 again, ny1, and z2 again. So we get the normal stress sigma x is equal to sigma x dash is equal to sigma n itself. Similarly, the shear stress components in this plane in x and y direction is obtained by the y dash, obtained by the projection in y direction. In a similar manner, we have tau xy, xyz, nx, ny, nx1 in ny2, ny1 in ny2. Here we are multiplying ny2 because it is subtended with the angle with y-axis, ny2 itself and z2 itself. That is not ny2, but is nx2. On the same time, if epsa1, epsa2, and epsa3 are the principal strain, which are also along x, y, and z direction of the normal strain in x dash direction itself. So, in this other condition, we can simply write epsa xx is equal to nx1 square, epsa1, nx plus 10, epsa2, nx2 plus epsa3, etc. The shear strain now we have already calculated here. The shear strain is now obtained from the equation here, on the equation formulated here, gamma x dash y dash 1 by 1 plus ex 1 plus y dash square, and these two nx and 1 2 epsa 1, n by 2 n epsa 2, nz2, nz3, epsa 3 itself. Now, what is found from this equation that this epsa x dash is and epsa y dash is extremely small compared to 1. So we can safely say this 1 plus epsa x ex1 epsa x1 dash into 1 plus epsa y dash is equal to 1 itself. And we have already calculated just a minute before nx2, nx1, nx2 plus ny1, ny2, nz1, nz2 is equal to 0. So this equation gamma x dash y dash is reduced to this should be an equal sign here. Gamma x dash y dash is equal to 2 into nx1, nx2 epsa 1 and y1 epsa 2 and nz2 epsa 1 itself. Now, we have in equation 4, we have got the values of sigma 1, sigma 2, and sigma 3 in terms of variance. So we can simply put the value of sigma 1, sigma 2 here. So